get dirtier. That's not what I'm saying. And this is why, okay? There's always a cause and effect. So if you think about it as a balance, you can see that if you clean your room, it's going from disordered to ordered. But you have to ask yourself, what around it is going from ordered to disordered to balance that scale to at least 0, if not more disordered, okay? So you can think about things like you moving around. What's that doing? Your movement is moving molecules and atoms around you. The more movement equals more energy. The more things move, the more energy they have, which means, as we saw, at the time when energy increases, it becomes more disordered. So just by you moving, you're adding more disorder around you. Okay, so that's starting to offset the orderedness of your cleaned room. What else is happening? As you move, what's your body doing? It's burning energy, right? And that release of energy, that heat, is increasing the energy, right? The heat is more disordered on our scale. If we're remembering our scale, if you're lying like a lump on the couch, you have a lower temperature. If you're moving around, cleaning your room really fast because people are coming over, your temp goes up, right? They might seem like small changes, but on the whole, if you start thinking about things that way in terms of the total universe around you, if you paid attention to it all, you would see that there are enough things going into disorder to balance the things going into order, okay? So on the whole, even though it seems like the idea of evolution seems totally like it's going against it, it's not necessarily going against the second law of thermodynamics. However, if you read through the book, they talk about the fact that although it doesn't prove it, it simply doesn't disprove these theories. Just because it doesn't disprove them doesn't mean that it's true, because they have to be able to come up with a mechanism to offset that disorder to order. And as of now, in the book author, Jay Wiley, he basically says, in his opinion, they still haven't found that mechanism to balance that, okay? So, all that being said, so we talked about delta H. Let me just recap really quick. We talked about delta H, which is the change in energy of reactions. And we talked about 2 ways to find it. Bond energies, writing out the little Lewis structures, kind of annoying, but happens. And Hess's law. It's the sum of the products minus the sum of the reactants, okay? Then we talked about, just now, entropy, disorder, change in disorder, okay? Which is the same thing as Hess's law. Sum of products minus sum of reactants, okay? Now, why am I telling you all of this? And here's, I'll go over this towards the end. So, what's the whole point of this? Well, the reason why we introduce these 2 things is because we need to be able to see that, you should be able to see now, that delta S is the change in disorder of something. Well, when that, just like your room, when you're cleaning it, what was happening around you in the environment? There was change of energy, right? So when we talk about the second law of thermodynamics, we are talking about both the change in entropy, disorder, and we're talking about the change in energy, enthalpy. Okay? So now we're going to bring all this together because we need both of these things if we're going to talk truly about the second law of thermodynamics of things either being equal or more disordered. We have to talk about both of them. We can't just talk about our substance because it's leaving off everything happening around it. So we're going to bring them both together, and this is how we bring it together with Gibbs free energy. Okay? So let me put up this guy right here. So Gibbs free energy right here. Gibbs free energy is going to be notated with a capital G. Okay? And so we're going to be finding the change in Gibbs free energy. And it simply is a way to put your change in enthalpy and your change in entropy, disorder, and change in energy together. Okay? Okay, so let's dive into Gibbs free energy. So, really, the whole idea between delta G, or Gibbs free energy, is just to determine if a reaction can occur in the world. right? Because we said in order for something to happen, the amount of disorder has to increase. So really, we're just looking to see, can this happen or not happen, okay? And they also called this spontaneous versus not spontaneous, okay? If it is spontaneous, we know it can proceed. So that just means, is it against the law of the second law of thermodynamics? If it's in accordance with it, if things go to a more disordered state, we would say it's spontaneous, it can happen in nature. If, however, it is not spontaneous, it goes against the second law of thermodynamics as a whole, and we would say it would never happen because it's going from a disordered state to an ordered state on the whole, okay, taking everything into account. So that's where we are with this. So this is going to be our way of determining it, okay? Gibbs free energy right here. We have our change in enthalpy, or change in energy, minus our temperature times our entropy, okay? So we're really going to need these two things to be able to run this. Now, remember, we're on all of these things, and I'll talk about these right before we end. So here's delta H, delta S, delta G. Remember, in all of these different things that we're solving for, we're either going to get a positive or a negative number. Positive, negative, positive, negative, positive, negative. For Gibbs free energy, our negative right here, if we get a negative number for an answer, that tells us we're good to go, doesn't go against the second law of thermodynamics, we're good. The positive tells us it's not consistent, it gets less disordered, and so we can't do it. So these kind of make sense. These seem to be opposite. So the way I remember it is G is for gangsta, and if you make your positive sign like this, if you get a positive outcome, you can't do it. It creates an X, a stop. So if you get a positive on the outcome for your thing, just remember, positive, nope, you can't do it. It's against the second law of thermodynamics. I don't know if that helps. Helps me. All right, so if you look, we have, again, just like we have before, we have a standard Gibbs free energy of formation table, table 13.4. Okay, this is our last table in our appendix. I label it with a delta G, and I remind myself, same as delta H, elements are equal to 0. So we have two different ways of finding delta G. Take a look here. So just like delta H, we had two ways of finding it. Delta S, we only have one way. Delta G, we have two ways, okay? And this is how you tell which one to use. You can use this table as long as it's at room temperature, which is 298 Kelvin, right here. So you can use the easy way, the table, if it's at that temperature. If it's not, then you have to use the other way. You have to use the formula, okay? This is the formula right here. All this is telling you is that when you plug these things in, they better be less than 0, okay? So, that goes along with this. Real quick, let me see, on page 447, they have all this like, well, it can be spontaneous if it's at a negative and a positive and a positive and a negative, blah, 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 blah. Okay, it might be a little bit confusing, but basically this is what it's telling us. I wrote it right here. This is the middle, top to middle of page 447. They're telling you that for this, if you're doing a reaction in a lab, which makes sense, it's not always at room temperature, okay? So this is not at room temperature. If you're doing a reaction, you can kind of predict what's going to happen, whether it's going to be against the second law of thermodynamics or for it, spontaneous, not spontaneous, okay? For example, and these are in order, okay? So this is your delta G, delta H, delta S. If you have a negative number here for delta H, and you have a positive here, it's always going to be negative answer. And remember, negative means good, spontaneous, it doesn't go against the law, okay? And that makes sense, right? Because if we change our signs in algebra, we chick, chick. So we make this a plus, this a negative and a negative is always going to be negative, okay? Same way here. If I have a positive delta H number that I plug in, and I have a negative entropy number, it's always going to be positive. So if I change the signs, Now I have a positive plus a positive. It's always going to be positive. And remember, when we have a positive G, it can't happen. It's never spontaneous. It won't ever happen in nature. You cannot run that reaction. It won't work. It goes against the second law of thermodynamics, okay? So if it's one of these two formats, a negative, positive, it's going to be negative, positive, negative. It's always going to be positive. If it's not one of these two, that means